Good morning, Cisco cohort. It's time to start today's particular lesson on access control lists. And I'm going to be using this grayed out slideshow from the course presentation materials. And it's entitled ACL Standard and Extended. We're going to talk about the concepts of Module 4, which is the concepts and theory of operation about how access list control lists work. And then we'll cover the Module 5, which is actually the iOS commands and code that we keyed to them to get our particular access control list set up that we desire our permits and denies to be put in there. Okay, hang on just a second and I'll bring up the presentation. So what are these darn ACLs? So an access control list is some lines of code that you type into a router. And what it does is it allows you to permit or deny devices, host machines with certain IP addresses. And this can be as particular or as granular as a single host machine with a single unique IP address up to a range of IP addresses, such as all the host machines on one network or one subnet, to any range you want, all the way from one machine to every machine in the universe. And all these access control list lines are going to do, what they're going to do is you're going to specify a range of addresses, and then you're going to tell it that if this machine is within this range of addresses, it's either to be permitted or to be denied. The traffic from him is to be permitted or to be denied. And we can base these on very specific conditions if we want to. We're going to apply these access control lists to routers interface ports on the inbound and outbound direction. So normally the router is going to examine every packet, and he's going to look. A normal operation of a router would be to, if there was no access control list, just examine the packet and determine what the destination network address is, and then look on the routing table to see if he has the knowledge of where to forward that packet to get closer to his destination. When we add an access control list function to a router, what we do is we also have it examine more things about the network packet. We can examine such things as, for example, with the standard access control list, we can look at the source address. With an extended access control list, we can look at both the source and destination addresses, as well as, for example, what port numbers are being conveyed on this particular segment of data, like it's port 25 for emails, at port 80 for web traffic, if it's at port 20 and 21 for FTP, support 22 for telnet, things of that nature. So we can examine on these protocols. So this gives us the ability, for example, permit incoming web traffic and mail traffic to our company, port 80 and port 25, but deny the other ports, like people trying to come in and telnet to our servers or routers. So access control lists are defined on a per protocol basis. Now, we used to have, what is this alarming, IPX and AppleTalk? Oh my. Novell Network uses a protocol called IPX. It used to be sort of part of the network CCNA, but it's been out for many years. AppleTalk is a proprietary protocol for AppleTalk Macintoshes that had a method of plugging them together. And I used to run a network. When I ran a network back in the 90s at the college publishing place, we had IPE for the internet. We had IPX for our Novell servers. We had AppleTalk with a bunch of Macintoshes doing graphical production. These days, it's much more common to only run one or two protocols, one or two of the IP protocols. That would be IP version 4 or IP version 6, or maybe both of them if you're running dual stack. So access control lists are defined on a per protocol basis. In other words, if I was running dual stack in my enterprise and I was running some IP version 4 and some IP version 6, I would define access control lists separately for the IP version 4 traffic and the IP version 6 traffic. Now, please note, access control lists configuration on IP version 6 are no longer a part of the CCNA objectives. We're just going to do IP version 4 access control lists. Access control lists also are defined on a per direction basis. You're going to choose a port on your router that's the best port to either filter the traffic on either inbound or an outbound direction. And so it's a per port, per direction, per protocol. So if I had one set of rules for inbound traffic and another set of rules for outbound traffic, I would define separate access control lists for each one of those functions and apply them to that interface, both inbound and outbound. So multi-protocols these days are not that common anymore, just IP version 4, maybe IP version 6. It's not like 20, 30 years ago where we had so many other protocols. Makes it easier for network administrators. I think the buzzword is everything over IP. So an access control list is a group of statements. It's going to set up, it's going to define whether packets are going to be permitted or denied coming into an interface or leaving an interface, because you can set up your access control list to be either inbound or outbound. They're going to operate in a sequential logical order. And we're going to see these lists of code in just a little bit. This thing's very theoretical right now. So each line is tested one by one. And as the packet is checked, as each line of the access control list is checked, if that packet, the address on that packet matches the address in the line, then either the permit or deny will take place. And the rest of the access control list statements in that list of statements won't be checked. If the condition match is not true on that line, for example, the IP address of the packet coming in doesn't match this particular line, he'll drop down, he'll check the second line. And he'll drop down, and he'll check the third line. He'll continue through the list until he finds a match. If he doesn't find any matches on any of the lines in the access control list, there's an automatic deny everything. It's there by default. It's not visible. So this means that all access control lists, if they're going to permit some filtered traffic, must have some permit rules in them, some permit statements, to allow some traffic to be permitted and all of the traffic to be denied. So they work in top-down fashion, sequential order from top to bottom. Once a statement is a match, which means the particular IP address of that packet being examined matches one of the addresses that's on the access control list line, then the rest of the statements are skipped. He just does what is at the end of that list, the permit or the deny. Only one access list per protocol per interface. You can combine functions together. You can, for example, I don't need one access control list to allow incoming web traffic, and I don't need a second access control list to allow incoming email traffic. I can write one access control list and just have one permit line that says permit port 80 for web. I have a second line that says please permit port 25 for email. But at the end of every list of access control list statements, there's always this implicit deny any at the end of every access list. Now, important function here, access control lists don't block packets that come within the router. So if you are plugged into the console port of the router and you start a ping or telnet or something, even if you have to go out to a certain interface to complete that ping, and that interface has an access control list applied to it that says no pings, since you're the man in the middle of the router there, you get out. The access control list doesn't apply to you. Access control lists only can block packets that came in to the router from one of the interfaces, and then he's on his way out of the router on another interface, according to what was in the IP routing table. So you can be consoled in, and he won't affect you. You can even be telnetted or secure shelled into the console of the router, and that will not affect you. There are two basic categories of access control lists. Let's see, we're taping. Oh dear, we timed out, hold on. Sorry, one of these things timed out, I gotta fix it. Gotta fix this. Stand by 1 minute where I fix my timeout on my attendance. Change it to high performance. Okay. There are two types of access control lists. We're going to first look at the more simple ones. They're called standard access control lists. The only thing they can filter on is what was the source IP address of that packet. The machine that created the packet, that's the source IP address. That's the only thing they can filter on. It's very simplistic. So if I want to say, oh, the boss's useless nephew has this IP address, don't allow him to go out to the internet and get on Facebook. Don't allow him to get anywhere on the network. I can just filter on a source address and block it. We'll look at those first and the concepts of how those work. Extended access control lists can filter on not only just the source IP address like a standard, they can also filter on the source IP address and or the destination IP address and or the port numbers and or protocols and many other parameters as well. This would allow us to do a more sophisticated access control list that, for example, permitted incoming web traffic on port 80 and permitted incoming mail traffic, email traffic on port 25, but denied other types of traffic. We didn't want to come in like a telnet attempt or a secure shell attempt. So we'll look at those second after we look at access control list, standard access control list. Now here's the syntax. We're going to be at the global configuration mode, and we're going to type the command access list, and we're going to look at some ranges for access control lists. There are access control lists that are numbered. The range for standard access control lists is from 1 to 99. Since that was if you need more than 99, that's pretty unusual. I don't see, unless it's a huge corporation, why you need more than 99 of them. Cisco put an extended bank of about 700 or 800 extra addresses in another range of addresses. So when you create an access control list, there's a two-step process. The first step is to find the list itself. You'll say access list 1, and you'll put a source address, and you'll say permit or deny, as many lines as you need to satisfy the logic of what security or what traffic filtering you're trying to do in your network. And once you've created the access control list, it doesn't actually take effect until you take step 2 and apply it to a port. So for example, in step 2, the prompt is changed to router config-if. He's gone to a particular port, like the G00 port, maybe the Ethernet port. And then he's going to apply that access group that he created back in step 1. Maybe he said access list 1, he'll say access group 1. And he'll apply that in inbound or outbound direction to that particular interface. There's the range of numbers. The only numbers that we're really interested in are IP, and you don't have to worry about IP version 6 anymore. That used to be an objective for CCNA. It was IP version 6 access control lists, but they're not in the CCNA routing and switching CCNA certification exam objectives anymore. So we're going to go to step 1, and we're going to define the access control list, and we'll say at the configuration mode of the router, the word access-list, and then we'll make up a number to use. Any number from 1 to 99. That's standard though IP version 4. And so there's an extra bank of addresses that you can use if you happen to need more than 100 of them. We will not be doing any AppleTalk, IPX, anything of that nature. We will be using, we're going to talk about standard first. And a little bit later, after we've gone through standard, we'll look at extended IP access control lists, which are access control lists that you can filter on more than just the source address. You can filter on the source and destination addresses. You can filter on port numbers. You can filter on protocols. But let's do our baby steps first, and let's get the standard access control list. Let's look at that first. Okay, so here is a sample small business. And this small business is, we have 3 different departments. We've got the administration department, we've got the sales department, and we got the engineering department. And each one of these departments is on their own separate network, their own separate subnet. Each one has their own switch, and each one of them has their own router, and the 3 routers are all connected together through their serial ports. So this is the internal private connectivity within the company for this. So let's look at an example here, and let's look at this workstation that has the red around the number, 172.16.3.2. And the rule here that the security rule or filtering rule that we've been told to implement, we've been tasked with saying that only that host that's encircled in red, in squared, rectangled in red, he's the only one that can create traffic that leaves the sales network. All of the other machines on the sales network, for example, they give a second host here who's 30.3. All the other host machines on the network are not going to be allowed. Their traffic will not be allowed to leave the network. And we'll be able to easily test for that rule by simply writing a statement that says, if your source address is 172.16.30.2, your traffic is to be permitted. Otherwise, it's denied. If you're not 30.2, you don't get out. If you're 30.2, you get out. So let's look at how we would do this with our statements that we talked about so far. Okay, I'm going to go to router B. Notice that our workstation, the one that has the red number on it, is connected to the sales switch and the router B. And we want to somehow allow him his traffic to go into the router and escape to the rest of the company network. But if address is not 30.2, it will not be allowed to proceed through the router and be routed to the other networks. So here's our test condition. Access list with the global configuration mode. Access list number 10, that's just an arbitrary number somebody came up with. It's between 1 and 99, and the range from 1 to 99 is reserved for standard access control lists. permit, we can say permit or deny. Well, we want to permit only this one address, 172.16.30.0. And that one line will do it for this particular logic we're trying to set up. However, this implicit deny any that's at the end of every access control list, it means deny all traffic. So here it is written out. Access list 10, deny, and what is 0.0.0.0 in networking? Remember our static routing statement, the default static route, we'd say IP route 0.0.0.0. 0.0.0.0, Ethernet 00, as a ways of specifying a static default route back to an ISP or a home office. Well, 0.0.0.0 in IP networking is like the wildcard that's it matches every possible address that could exist. Any combination of a 32-bit binary value, a dotted decimal value matches that. It's like in the DOS, the Windows DOS environment, if you type delete ***, that means *** is the wildcard, that means delete all the files. So if I type delete *** and press enter, it would delete all the files in that directory. So to specify this particular, this 0.0.0.0 means deny every possible address that could exist, deny him. And by the way, what's his wildcard mask? What's his subnet mask? Well, 255.255.255.255 is a special wildcard mask that says, I don't care what subnet mask you got. Any subnet mask you've got, you're still going to be denied. I'm not going to even look at the subnet mask. I'm just going to look at the address. And if you're any address, you're going to be denied. So any address, any subnet mask is denied. So if the workstation here sends out some data to the router's going to say, oh yeah, look, his source address is 172.16.30.0. The first line matches. So all the traffic that comes from this machine with the rectangle red number around it, 172.16.30.2, his information will be allowed to pass through the router because we put this code in here of filtering traffic, and it says don't filter around, let him go. If it's any other address, for example, the 30.3 guy, if you're 30.3, well, that's not 30.2. Then you match the second line, your traffic is denied. So effectively, the only workstation here, the 30.2 workstation, maybe it's the sales department supervisor. His is the only one allowed to communicate with the rest of the company network. Everybody else is denied. So that's the effect of this first simple standard access control list we look at. Now we've defined the list, now we have to apply it to an interface. The question is, which interface do we apply it to? Do we apply it to an inbound interface, that upward bound arrow going into router B, Ethernet 0? Or do we apply it outbound to the 00 port going back to the administration network? Or do we apply it outbound to the network arrow going to the right back to the engineering department? So far we have defined an ACL, we have not yet applied it. It will have no effect until I actually apply it to a router's interface. So there's a rule of good practice, a best practice, but because standard access control lists are so clunky and the only thing we can filter on is the source destination, source address, then we have to apply that standard access control list to the interface closest to the destination of the traffic. If it were an extended access control list, we could be much more subtle, and we could be, and not, apply close to the source machine that's a troublemaker and nip them in the bud. But we can't do that with standard access control lists. So we're going to start with standard, and then we'll do it later with extended and see how much easier, not easier, but how much more configurable and how more granular you can get with extended access control lists. So the definition of out is traffic that has been routed by the router. It's already gone through the routing table process, and it's leaving the router. So these two arrows to the left and to the right coming out of router B, that's traffic that's proceeding in an outbound direction. Traffic has already gone into the router. It's gone through the IP routing table lookup process. It's ready to be assigned to an outbound interface, and it's going to go out that interface. If there's an access control list there, then it has to go through the filtering of the access control list. The alternative method is to put the access control list on the inbound interface. In this case, it's the default gateway router address for everybody on the sales network. It's 30.1. It's 172.16.30.1. So all traffic that comes from the sales network that needs to be routed to the other networks, he has to go in that default gateway port for this particular network, and then the router will look in this routing table and make the traffic forwarding decision. Of course, he has to respect access control lists. It's more efficient to filter the traffic in the inbound direction and get rid of traffic that you're not going to route anyway before it goes to the routing table lookup process, because routers spend almost all of their CPU cycle and performance cycles doing the routing table lookup process. So if I can filter it before it goes to that routing table lookup process, it's going to be more efficient. If I have to wait till traffic goes through the routing table lookup process and then gets assigned to an outbound interface and then gets filtered, I wasted a lot of CPU cycles. So it's better if we can apply it to inbound. So in this case, let's do that. Let's apply our access control list to the inbound to the Ethernet 0 port, where the red upward pointing arrow is in our graphic. So we have done the access list 10 permit, the implicit deny any. We don't have to type that, but it looks like the middle there. Okay, let's go to router B and apply our access control list to that Ethernet port in an inbound direction. We're going to specify Ethernet 0, and we're going to apply our access control list to that IP access group 10N. And you can't see it because it's hiding behind this graphic here. But the line of code is IP access group 10N. Now, alternatively, we could have done it on the two outbound interfaces, and it would have achieved the same effect. It would have only allowed the 172.16.30.2 workstation, the supervisor, and the sales department to get to the other networks. It was more wasteful because all the packets would have to go through the routing table lookup process that aren't supposed to leave, and then they get killed by the access control list. However, there's an unintended thing here that's going on, because the implicit deny any, this access control list would only permit the manager to get to the administration network and engineering network. However, it's also going to block all kinds of traffic, legitimate traffic otherwise, from engineering to administration and administration to engineering. Oh, that's blowback. That's an unintended consequence. We didn't think about that. So we can't use this outbound on the two serial ports that go to the networks. It would work for blocking the traffic from the salespeople that aren't supposed to get out, but it would also block other traffic that we want to get out. So this is the form we're going to use. We're going to apply the access control list to router B in the inbound port on the lower Ethernet port. And we're going to say IP access group 10 in, and all inbound traffic to that router, that port E0 on that router will be checked. And if it's 172.16.30.2, it will be able to go on its way. If it's any other address, it will be blocked. It will be denied. It'll be filtered. Okay, now let's change the rules. Let's say that besides the sales manager, the four most productive sales force, and they have the workstations 172.16.30.2, 30.3, 30.4, and 30.5. They're all going to be allowed to create traffic and leave the network. They're the only ones that are authorized to enter sales into the sales computer over the administration side and look at the engineering department and see the specifications and the blueprints for the next generation software product that they're putting out. All other host machines in the sales department, if they're not .2, .3, .4, or .5, they are to be denied. Okay, so it's a /24 network. There could be up to 250 odd machines on this network. He's only showing 2 in the diagram. So let's expand our slide that we came up with last time and come up with a way of specifying any one of those 4 permitted addresses, .2, .3, .4, .5. Well, I'll simply add, we already have this one, right? Well, let's add these 3 other statements. .2, .3, .4, and .5 are to be permitted. So if you're .2, you match the first line. If you're .3, you don't match the first line, it drops to the second line, it matches you and you're permitted. If you're .5, the first 3 lines don't match you, but the fourth line, your address matches you and you're out. If you're any other address, if you're not exactly .2, .3, or .4, or .5, you will not match any of the 4 bold lines, and you will drop to the implicit deny any, and your traffic will be blocked. We place it exactly in the same way. We go to the Ethernet 0 port, and we apply the access group 10 that we just created in an inbound direction, where that red arrow is pointing up, going into router B. So now we successfully changed our access control list to allow 4 arbitrary addresses and everybody else to be blocked. Okay, let's say I want to get rid of the access control list. In the iOS command language set, most commands can be reversed or negated and then be made to as if they never existed by repeating them and putting the word no in front of them. So if I don't want access list 10 in there anymore, remember we just had an access control list that had 4 lines. We want to get rid of that. Okay, we don't want this anymore. So I'm going to just say no access list 10 and it'll get rid of the access list. However, it's best practice that since there's 2 sets of statements in an access control list, one to create the permit and deny test conditions and one to apply it to an interface, we should go back to that interface ER0 config-IF and say no IP access group 10 in, because before we said IP access group 10 in. That will completely remove that from the router. That's the safest thing to do. Okay, now we have a new scenario. And in this scenario, the guy that's got the 172.16.30.2 workstation, he is the boss's nephew. He's worthless. He's only there because his boss, the owner of the company, got him a job for the summer. All he wants to do is go on Facebook and screw around and not do any useful work. He's not going to create any sales for the company. So it's okay. The boss said he could sit at the desk and be there, and but we can't allow him to have any access to the network because he took a hacking course. He might try to break in and do something weird. So the decision has been made that whatever IP address he's got, and the boss's nephew has got the 172.16.32 workstation, he's not allowed to generate any traffic and leave. He can play solitaire on the computer. He can't go to Facebook. He can't mess around with the administration computer and try to hack into it and issue himself bogus checks. We're not going to allow that. So he is not allowed to go on the network. All other IP addresses in the sales department are allowed to leave the network. And we're going to talk about any keyword that can be used to represent a whole broad range of addresses. Okay, so let's say this. Let's go to router B and create an access list 10 and deny the boss's nephew. That's his individual IP address. Now we're going to put a second access control list that says permit any address in the world. So if the boss's nephew creates traffic and it tries to leave the network, he's going to be denied because he has that specific source address, 172.16.30.2. Any other workstation on the network, well, they're authorized by upper management to have access to the rest of the company. So if they have 30.3 or 30.4 or any other possible address, they will not match this statement. And the processing will drop to the second line. And the second line says, permit everything. I don't care which address is permitted. So that's how you filter one, deny, and filter or block one traffic only, one particular arbitrary IP address, and permit other addresses within a particular network. Then we'll apply it in the same way to the Ethernet port. Apply it as an access group number 10 to the inbound port of router B. So that way, I've allowed one arbitrary number and blocked everybody else. I've allowed a range of networks and blocked everybody else. And now we are blocking one particular troublesome host machine, but allowing any other address to go through. Now, what if we had put this in a different order? What would happen here? Order is very important. So say you're anybody else in the world and you fit this first line and you have any IP address, you're permitted. But if you're the boss's nephew creating some hazardous traffic, you would match the first line. It would no traffic could possibly come into the router could ever go past the first line because the first line says permit anybody, I don't care which address is. It would never go down and process the second line. So order is important. It has to be with the reverse order like we first come up with. So when traffic is applied, when an access control list is applied to an inbound interface, the packets go into that interface, and before it's allowed to proceed to the routing table, to go to the routing table lookup process and be assigned an outbound interface, an egress interface, first of all, the packets are going to be checked against. Then we need to see if they're going to survive the trip through the access control list. If they're denied for any reason, the packets are immediately dropped. They don't proceed to the routing table lookup process. This is why inbound access control lists are much more efficient than outbound access control lists, because we save the processor of the router a bunch of extra processing power to do this cumbersome multi-cycle performance hit base lookup process, and then eventually just discard the packet anyway. Okay, once a packet has been denied by an access control list, as a courtesy, the router will send back an Internet Control Message Protocol administratively prohibited destination unreachable to the machine that created the packet, just so he can interpret that as an error code if he needs to. Okay, Cisco says that traffic coming from the router is compared to access control list entries based on the order that the entries occur. I can add new statements, but they will only appear at the end of the list. We'll talk about the, oh yeah, there's a big gotcha here with the, if you have to re-edit the list, you might have to just delete it and re-enter it all again. The router will keep looking one by one through each statement until he finds a match. If there's no matches found, there's the implicit deny any. So for efficiency purposes in the router, it would be better to put the frequently hit entries at the top of the list so they'll be processed more quickly. Implicit deny for all traffic that's not permitted. So if I only have one single access control list and it's only a deny, that means all traffic is being denied. So all access control lists must have at least one permit statement in them somewhere, or all traffic would be blocked at a very expensive in CPU cost. It's much more if you just want to block out traffic, just to do the shutdown command on that port. Now let's look at wildcard masks. We looked at wildcard mask with OSPF as an alternative method instead of specifying the subnet mask of 255.255.0.0. We specified a wildcard mask of 0.0.255.285. It's a sort of a mirror image of the subnet mask. So in access control lists, the wildcard mask tells us how much of this address needs to be checked to see if it's to be matched or not. The zeros mean we must check that octet. So in this case, the 172.16 are the first two octets of the address, and the zeros tell us we must check. And if the address is 172.16. anything else for the last two octets, this is a match, and this traffic is to be permitted. The ones in the wildcard mask tell us I don't care what those bits are. So that means you have to be 172.16. You have to be 172.16, the first 16 bits. The remaining 16 bits can be any possible value. So that means on the Class B, legacy Class B network of 172.16, it can be any possible address on that network. So a wildcard mask is a 32-bit quantity, kind of like IP addresses are 32 bits, subnet masks are 32-bit. Wildcard masks are 32-bit quantities divided into 4 octets, paired with an IP address. But the ones and the zeros have different meaning. In the subnet mask, the ones tell us these are the bits in the network address. That's the network prefix portion. And the zeros in the subnet mask tell us this is the however many zeros there are, tells us how big this network is. The host bits, if there's 8 host bits, /24 to the power 8, 256 possible addresses. In a wildcard mask, the ones and the zeros tell us this other purpose I just mentioned. If it's a 0, it must match exactly. If it's a 1, I don't care what it is. So generally speaking, you can take the subnet mask for a network and simply change all the 255s to zeros and all the zeros to 255s, and you'll have your subnet, you'll have your wildcard mask. So it's kind of like an inverse subnet mask or a mirror image of a subnet mask. So here we have an address of 172.16.0.0, and here's our wildcard mask, and here's all the zeros. This means must match exactly. Here's the binary pattern for 172.16. These zeros means those first 16 bits, the first half of this IP address, must match exactly. Must be 172.16, can't be 15, can't be 17. Must be only and exactly 172.16. The ones in the wildcard mask mean I don't care what those bits are. They can be any possible address. So matching packets will be 172.16. Anything in the world, any arbitrary 8-bit value you can put there, it's going to match. So 0 means check, must match exactly. 1 means don't check, don't care. It can be any value. So when we take a wildcard mask of the rest of 172.16, that means the 172.16 must match exactly. The last two octets can be any possible value, can be any possible number. Now, let's use wildcard masks and permit the entire sales network, which is 172, the sales network, these guys here, they're all 172.16.30. something. And the 172.16.50.2, that's the engineering supervisor, engineering manager. We want them to be able to have access to router A. We want all other traffic to be denied from entering the administration network, because the administration network has a server on it, and we don't want the boys messing around with it, trying to break into it. For example, the boss's nephew. Okay, let's create an access control list then that permits the entire 172.16.30 network and the individual host machine on the 50. network, and denies all other traffic. Let's look at the first line. Access list 11, permit 172.16.30.0. Well, everybody on the sales network is 172.16.30. something. The wildcard mask means you must be 172.16.30. anything to match this line. Everybody on the sales network will be one of those numbers. They'll be 30. some value, .2, .3, .4, .5, whatever value they got. They're going to match that first line. They will be allowed to access the administration network because they got to key in sales orders to the administration computer. The other requirement was this host workstation right here, the engineering supervisor manager, only his individual workstation, 172.16.50.2. Well, look at the second line. It says permit 172.16.50.2. And what do the zeros mean in a wildcard mask? Must match exactly. So the 4 zeros tell us that that entire address must match exactly 172.16.50.2 to be permitted. Everybody else's address is denied because of the implicit denial. So now we have allowed all the PCs in the Salesforce and the one engineering supervisor manager PC to be able to access the administration department. Well, we got to apply it to a port on router A first. We permitted the access control list. We created the access control list, but now we have to apply it to one of the ports. So let's apply this access control list to an interface. Let's go to interface E0 of the first router and apply it in an outbound direction. We could do that. This is a forced little pipeline here that this data has to go through to get to the administration network. So we'll go to interface E0 IP access group 11 out, and we've applied it. Now let's look at the any keyword. Before we said deny 0.0.0.0.255.255, deny all possible addresses. As a shorthand, you can use the word any. Instead of having to type out all those zeros and all those periods, and make sure you don't make any typographic errors. So I can shorthand and say access list 11 deny any, and that will do exactly the same effect. So if we had example 3, we were to deny 172.16.30.2 and permit all other addresses, we had the option of either using the shorter line to type it in or type in this long line. So permit any is a nice handy shortcut syntax you can type in, so you don't have to type in so many numbers and periods. Now there is another shorthand called the host option. Normally, if I wanted to access, let's say I wanted to permit, I'm only permitting the 192.168.1.100 device in a particular scenario network setup. And 0.0.0.0 means must be exactly that exact 192.168.1.100 to match that line. You are allowed to type, instead of having to type in so many zeros and periods, you can type the word host 192.168.1.100 and it'll take it as if you typed it in using the first line. As a matter of fact, you can even leave out the word host and it'll interpret it. It's the same thing, one individual host address. So it's a sort of a shorthand method of looking at what's going on there, typing in configuration. Now, how do we check or verify an access control list after we typed it in? I can type show IP interface on one of my interfaces and it will show me in this case that there is an inbound access control list, number 2, and an inbound control on the fast Ethernet port. And there's an additional inbound access control list on the serial port. Now we know from the value of 2 that this is a standard access control list. We've only done standard so far. We're going to do extended in just a little bit. And we know in this particular case, it's 101. That's one of the reserved range of addresses. 100 to 199 is the reserved range of addresses for extended access control lists. Don't worry, we'll cover how they're set up in just a little bit. I can type show access lists and see all the access lists that are present on this particular router. We have our standard list 2 and our extended list 101, and it shows you the actual checking code, the statements code that are checked for condition, the condition codes that are checked for on this particular router. You can have one, it is possible to create one access control list and apply it to more than one interface. Technically, it allows you to do that. You're probably going to have different conditions for each interface, but it will allow you to do this. Now let's look at access control list operations, and let's look again at inbound access control list. Normally, a router will receive a packet, and he will look at the destination network that's in that packet and look in his routing table to see if he knows where to choose the best path for it, to route it to the best destination port to be on his way. If we have an inbound access control list, we're going to interrupt this process. When the packet comes into the router, before he gets to go to the routing table lookup process, he has to survive and be permitted by the access control list first. So in this case, we applied to the Ethernet 0 port, we applied access group 11 in the inbound direction. So in this flowchart, we see that he tests to see, well, this is an IP packet. Okay, it is. Well, this is an IP access control list. Is there a standard access control list on this interface? Yes, it is. Does the source address of this packet match one of the lines that has a permit in it? Well, yes. Is it be permitted? Well, yes. Go to the routing table lookup process and route it. If he goes through the lines in the list and it doesn't match the first line, and doesn't match the second line, and doesn't match the third line, doesn't match the fourth line, if then our implicit deny any, he keeps moving to the next statement until he runs out of lines. Oh, it's the last line now. Does it match? It didn't match any lines. What do we do with it? Throw it away, send the destination not found, Internet Control Message Protocol, ICMP, back to the host machine. And it doesn't go through the routing table lookup process. It wasn't determined to be acceptable for that range of source addresses to be processed by the router. Okay, so standard access control lists have an available range of numbers from 1 to 99. They only filter on the source IP address. And we're going to use wildcard mask. And we have to apply standard access control lists closest to the destination because they're so clunky and they only filter on the source address. We have to apply them closest possible to the destination machine being protected. That's why in that previous example, we couldn't use the serial ports because we protected against the boss's nephew, but we inadvertently blocked legitimate traffic between the engineering department and the administration department. Again, if I want to get rid of an access control list, I just put no access list 11 or whatever rule was in there, access list 2 in this case, in this top of this chart, and the whole thing will be deleted. Now let's look at extended access control lists. Extended access control lists allow us to filter not only on the source address, but also we could use the destination address. We also use port numbers like port 25 for email, port 80 for web traffic. So this is much more of a powerful dual-edged sword that we can use to more granularly filter traffic in our network. And maybe upper management has set a rule that we only want inbound traffic coming in from the internet to our internal data center. We only want traffic to come to our website so they can buy our products, and we only want traffic to go to our email server so they can send email to and from the company employees with our trading partners. We can do that kind of filtering with an extended access control list. We can't do that with a standard access control list because he doesn't have the ability to filter on anything except what address did he come from. He has no concept of, oh, is it web traffic or is it email traffic? But with extended extended control lists, extended access control lists, we can look for that sort of a thing. There is a predetermined range of addresses or list numbers from 100 to 199. We talked about standard access lists are IP, 1 to 99. Extended IP is 100 to 199, and there's an extra range of 7 or more higher up in the list if you need them. Fortunately for us, no more AppleTalk, no more IPX. The Novell stuff is, I used to manage Novell stuff for years and years, but it's considered obsolete now. We go with Microsoft Windows Server and stuff, or Linux servers. So extended access control lists are more useful because they have a greater range of control. They have more granularity of control. They can check for source and destination addresses. They can check for protocols and port numbers, so they're more flexible. So I can permit or deny traffic based upon where did the packet originate and what is its destination, as well as what protocol types he's running. So I can allow the web, and I can allow the mail, and I can deny other traffic. Very flexible. So here's the syntax. We're going to go to the global configuration mode and give the command access list and give a number, and that's going to be between 100 and 199, and either permit or deny. And then we can put in the source address and or the destination address and or the protocols. What protocols can we filter on? Well, how about the entire IP family at layer 3? How about the entire family of transport layer protocols, TCP and UDP? How about Internet Control Message Protocol? We can filter on quite a few things. We can also filter on, I could say equals port 80. I could say not equal to port 80, and all traffic except web traffic would be allowed. So it's a very, very flexible. Here is an example. We have an access control list 114, which means it's extended. And it says, let's permit all TCP traffic that's telnet traffic if the source address is 172.16.6.0, and our wildcard mask tells us the source address can be 172.16.6. Any number in that fourth octet. So it's a whole subnet, a whole network we come up with here. The second line permits FTP and FTP data traffic. Second and third lines. FTP is a weird bird protocol. He uses port 20 and 21. So you got to permit both ports 20 and 21 or FTP won't work. Telnet's port 23. It just needs one port to work. Web traffic is 80. It only needs one port 80 to work. Email is 25. It only needs port 25 to work. There's a couple of weird protocols that use 2 port numbers, like Dynamic Host Configuration Protocol and the FTP use 2 port numbers. So we still are, even though it's extended access control list, we're still only permitted 1 access control list per interface, per direction, per port. And once we've created this list up here, we're going to apply it to an interface just like we did with the standard access control list. We'll say IP access list, in this case, number 114, in an inbound or outbound direction. Okay, let's use this in principle here in practice. We want router A, the router that's on the left-hand side of the diagram that connects to the administration department. We only want the engineering workstation, the engineering manager guy who's circled in red, 172.16.50.2. He's the only guy who should be able to access the web server in the administration department. Who has that address 172.16.10.2 and port address 80. He must be trying to get to the Internet Information Services web server that's built into that Microsoft Windows server in the administration department. All other traffic is to be denied. So only the engineering workstation can get to that square red server on the left, and only port 80 web traffic. He can't telnet, he can't send mail, he can only do web traffic. So how would we do this? Well, access list 110 extended, permit TCP from the TCP family of products. If it's port number 80, that's web traffic. Only the host machine 172.16.50.2 can create or source the traffic, and only the host machine 172.16.10.2 can be the destination traffic. If you have any other source address or any other destination address or any other port value, you will not be matched and your traffic will not be allowed to get to that server. So where should I place this access control list? Should I place it on router A? Should I place it on router C? Well, it turns out that for extended access control lists, since they're much more flexible and much more granular, it's better practice to place them as close as possible to the source machine that's allowed to do the traffic. So what if we wanted router A to permit any workstation on the sales network to be allowed to access the web server in the administration network, and all other traffic's denied? So what's the business case here? Well, everybody in the sales department should be able to key in orders to the web-based order entry data system that has been implemented over the administration server, the one in the square red. So only people in the sales department can access 172.16.10.2 port address 80. Let's write an access control list for this. Well, look, router A, access list 10, access list 110, extended, permit 172.16.30.0, and notice on the wildcard mask, the allowable addresses that would be permitted by the statement will be 172.16.30. Any number in the fourth octet, any possible number on that network, which are everybody on the sales network. That was our instructions from upper management. Only the sales network people can key orders into the administration server. The destination machine is the individual host address, exactly 172.16.10.2, and only port 80 traffic. Then we're going to apply this to the Ethernet port on router A in an outbound direction. Now, the context-sensitive help that's built into the Cisco iOS is pretty cool, and it allows you to, if you can't even remember the name of the first command, just type the question mark, and depending on whether it's the user exec mode or the privilege exec mode or the configuration mode, you'll be given a context-sensitive list of the commands that you could type depending on what level you're at, what your privileges are. And maybe you type, maybe you remember that to show something, you don't remember what the next word is. You can type show space and a question mark, and it'll give you all the things you can show at that particular level of access. So when you're doing access list controls command, that's pretty long. You can type access list, and then you forget what the range of number is. You can type the question mark. It'll tell you, oh, 1 to 99, 100 to 199, and so forth. So you can walk yourself through the command with the built-in access control list. So just the same as with standard lists, if it's an inbound access control list, the iOS will check the packet before it goes to the routing table process. If it's be permitted, it will go and be looked up by the routing table and sent on its way. If it's be denied, it'll be dropped. If it's an outbound access control list, the iOS has to wait to check the packets until it's been assigned. It doesn't know to what exit interface port this incoming packet will be assigned to by the routing table lookup process. So he has to wait to be assigned. And then if there's an access control list that's been applied to that outbound port, then he'll check it and permit it or drop it. That's less efficient because he had to go through that cumbersome routing table lookup process, and we'd like to reduce that as much as possible and use inbound if we can do it. It'll be a lighter load on the router. So the last entry is sufficient because in this case, the first three entries, they're all 10.1.1.2, and the host addresses are 170.16.10.1. We're permitting let's telnet port 23, and we're permitting host traffic, and we're permitting TCP and UDP traffic. I could permit all this stuff by saying permit IP. IP is a layer 3 protocol. All layer 4 traffic, regardless of whether it's TCP or UDP traffic, will be encapsulated in an IP packet at layer 3. So we could simply permit or deny traffic at the layer 3 layer and have one line instead of having to type 3 lines and do these 3 separate protocols at the transport layer. So if you can reduce the complexity of lines of code in a routing configuration table and it still achieves the desired security or filtering effect you knew it wished to take place and it worked, that's always a better option if you can lower the number of lines to be processed. Named access control lists were released as an alternative to having to say 1 to 99, oh, it's in the standard. 100 to 199 is extended. So we can give them mnemonic type names instead of having to use a number. And it has some other advantages. That eliminates the normal about 800. There's a limitation of about 800 standard or 800 extended access control lists. We can modify them without having to completely delete them and reconfigure them. We can put statements at the end of a list, but we can't delete the statements. If we need to really scramble up the statements, we're going to have to copy and paste to do it again. So the standard method for doing this was, if I need to change an access control list, I would copy and paste it from my show run statement to Notepad, like a text editor. I would rearrange the statements. I would delete the original list of statements from the router and then reapply the corrected, reordered list back. Easy to do with copy and paste on a Windows machine. So the syntax for access control lists is, we're going to use the syntax, be it the global configuration mode, and say IP access list extended, and the name is server access. I had to tell them it's extended because I didn't give them a clue anymore. 1 to 99 is standard and 100 to 199 is extended. I have to tell them it's an extended IP access list, and I'm giving it the arbitrary name of server access. And this particular access control list permits simple mail transfer protocol and domain DNS lookup traffic to be permitted from any host machine to a particular target server. Of course, the implicit deny at the end is deny IP any, and the log statement says, put this in the log so I can check everybody who's been denied, increase the security on my network. So we've applied the list, we've created the list. Now we need to apply it. It's being applied to the Ethernet port 00 in an outbound direction. So that way, instead of having just a crazy number, what does that mean? You can make up a mnemonic name like internet access or the deny telnet, or whatever name you want to. So in named access control lists, other than that name process, it's going to be the same thing of source address, destination address, protocols that became filtered or permitted. So here, when we have an IP access list that's been defined. It's a standard access control list. And they made up the mnemonic, it's an internet filter. Well, good, because when I come and look at this 6 months from now, I don't remember what this did. I can put a name in there that gives it some meaning. Then we have another access control list that's an extended one, and it applies to the marketing group to permit or deny traffic from the marketing department. So as a general rule of best practice, standard access control lists, since they do not specify destination addresses, we need to put them as close as possible to the destination being protected against this access control list. The problem is the traffic goes through the entire network and only gets blocked at the very end of its trip. And we've wasted all that precious bandwidth that we're paying for, least bandwidth from a service provider. Extended access control lists, we put them as close as possible to the source machine being denied. In this case, let's say the boss's nephew was working at this 10.00 network. That way the traffic is nipped in the bud and never costs us precious bandwidth that we're leasing back and forth from our various branch offices. So best practice, if it's standard, as close to the destination. If it's extended, as close to the source. So we can put access control lists in the best location and do our security and filtering of traffic what we desired, and make the network more efficient and not waste so much bandwidth. We want to increase efficiency of the network. Now let's look at firewalls. A firewall is it's essentially a router on steroids. It has multiple interfaces. And what we're going to do is we're going to program the firewall, and you can program Cisco routers to do some firewall functions. They're not a really sophisticated firewall like Cisco's Firepower product or other manufacturers like Palo Alto and make firewalls as well. It's a device that will allow certain traffic to pass and other traffic to not be passed. We've already learned how to do this. We can permit web traffic on port 80, and we can permit mail traffic on port 25, and we could deny other traffic from any arbitrary range of sources to any arbitrary range of destinations. So on firewalls that protect us from the outside world, we can use access control lists to permit a very common way that the intruder would try to come into your network and break in would be to pretend to be an internal IP address at that network. Example, at Tarrant County College, all of our Ethernet attached workstations have the source address of 10 dot something. In our SBUS 1125 classroom, everybody's 10.144.100 dot some address. So if I could pretend to be 10.144.100.2 and pretend to be in that classroom and somehow squirt my packet into the network, it would be treated as if it's a privileged internal trusted host machine, not some external attacker that's trying to break in. So we can program our firewalls to deny these types of traffic. We will typically are going to deny any public IP address. For example, 10.0, the 10 dot network is the Class A legacy, Class A reserve network range for private inside addresses. We'll use network address translation to translate those into a real address on the outside world. We'll get that. We'll do that next week. 172.16 is the legacy Class B private inside address range. We use that in our Wi-Fi network. 192.168 is the legacy Class C private inside address that most home routers use. Almost every home router I've seen is 192.168.1.1. So in the text, he's talking about RFC 1918. That was the request for comment that said, let's just set aside a few small limited range of networks for internal company use inside the network. So if the company changes ISPs or something like that, they'll have to completely readdress all of the network addresses of all their devices inside their network. And you don't want to have to do that. That's a big hassle. You have to change everybody's IP address. So an IP packet coming into our network should never have a source address that belongs to our network. So any packet that's shot into the Tarrant County College network from the outside world, he's pretending to be 10.144.100 or something, that won't be allowed. The firewall will block it. That line will block any 10 dot anything from the outside world. Only a legitimate inside traffic, which is on the inside of the router, will be allowed. So Cisco has some white papers that talk about things that ISPs and companies can do to sort of clean this up. Okay, we're almost done. Let's look at restricting virtual terminal access to a router. There's a special sort of a subset of access control lists, standard access control lists. And what we want to do is who should be able to telnet or secure shell into the router or the switch from another location, a remote location, and do some configuration or mess around with that switch. Only authorized IT technicians and engineers should be able to do this. So there's a special form of the access control list you can create. In this case, we have a company where all the authorized IT people up in their IT center, they all have the source address of 172.16.1. something or 172.16.2. something. If they have any of these two ranges of addresses, about 250, 500 addresses, they're to be permitted. They're going to be permitted to try to telnet into the device. Of course, they have to know the password and all that other stuff. So when I configure the access control list and apply it, of course, we always do this. We always do line PTY04. We always do login. We always do password Cisco or whatever it is. But if I add the line access class 2, this is this code right here, you will only be allowed to telnet into this device if you have one of these 500 possible IP addresses that are listed here. This has the effect of increasing network security. Network security is like layers of an onion. Well, I have an access control list layer of the onion. I have a password applied as a layer of the onion to make it more difficult to connect to the router if you're not an authorized user. Now remember that ACLs do not block packets that originate from within the router. So if I'm able to telnet or secure shell into a router or switch, and the access control list was applied, and I came from a legitimate computer in the IT department, I had that IP, I had the access, I had the IP address that was allowed. I go ahead and I'm into that router. So if there's other access control lists on that router that do not permit pings or whatever, that doesn't apply to me. It's as if I had plugged into the console port of that router and I have full outbound access. It has to be traffic that comes into the router from one port and leaves on the router from another port for an access control list that's either inbound or outbound to be applied. Okay, hang loose. I'm going to stop the recording.